start recording this session right now. Just like last night, I know some of you were already here last night, and so, well, thanks for coming back again. I guess it must have been okay the first time. But just like last night, I'm going to start off with just a couple of words of wisdom about Monday and the test. So this will be a little bit repetitive for those of you who were here last night, but just in case there's somebody who didn't catch it, I'm going to very briefly say a few words, and then we're going to spend the rest of the 2 hours, which should be most of it by far, doing some more practice problems. We're just going to do even more practice tonight on some different examples than the ones that we did last night. Okay, so again, I have not written the exam yet. So your best bet for a model of what to be expecting on Monday is going to be to look at the sample midterm that is in the Canvas page. And so if you do that, you will be able to get an idea like how many questions, how's it going to be structured, and all of that. I am going to show up on Monday into this classroom probably 15 minutes early at least. So I'm going to try to get here early just because I know it may take you guys a little bit of time to get the webcams going, and I'm going to obviously have to get you the exam. Which means that then you have to be able to like load it up and get yourself set up to start looking at it. So I encourage you, if you can, come a few minutes early so that you're not using the actual class period to handle some of those technical issues. Likewise, at the end of the exam, I'm going to give you some extra time to just get things like compiled. I know that some of these scanners do take a while. So I will let you work on the actual exam all the way until, 5:15 that we're done, and maybe even a little grace period after that. And then on top of that, I'll give you time to scan your exam in. So you hopefully will have plenty of time to, deal with the technical aspects. I know this is not ideal, what we're dealing with this semester with the remote exams, but I'll try to give you extra time to deal with all of that, but still have like an entire full class period, and then maybe even a little more than that to actually take care of the exam itself, okay, and to work on the test. There will be a folder in Canvas for you guys to submit those exams into, and then you'll be on your way. So that's kind of the game plan. The test, as you know, is basically covering everything that we've done up until this point, this first third of the semester that we've done. And that's primarily material from chapters 2, 3, 4, and 5 from our book. Just to reiterate, the things that we did in the lecture are the most important. And the review packet that's in Canvas highlights those particular things that I want you to know about and to be able to do. And those will all be things that we did in class. So there may be an occasional thing in the book that, kind of a tangent topic that maybe is interesting, but that we didn't really go into. Probably don't need to spend time studying that right now anyway for this exam. Okay, so focus on the big ticket stuff. Chinese remainder theorem, Fermat's little theorem, Diophantine equations, linear congruences, properties of primes, factorizations, all those kinds of things. And it's all in that review packet for you, kind of as a way to have it all in one place. If you like structure, the review packet is structured, so you can actually think of it as a checklist and go down and make sure that you are solid and confident about everything that's in that checklist. Okay. And then beyond that, just try that sample midterm. Maybe sometime tomorrow you can sit down and give yourself an hour and 15 minutes to an hour and a half. Just see what you can do. Try to do it without looking at the solutions as much as possible. And then, you can always check the answers after the fact. Okay. So that would basically probably be my best advice. We also have group works to look at, the first 5 group works, and then all of the practice quizzes that pertain up to week 6 There's only 3 of them actually, but they have some good questions in them that would be worth practicing, I think. And then we have had 5 homeworks. By the way, on the homework that you turned in last night, I have posted the solutions to it already, and I've graded about 3/4 of them. If you haven't gotten feedback on that homework yet, you will by the end of this evening. So I'm almost done with the grading. I'm going to finish it actually after our review session tonight. So you'll have all of that stuff available to you, the first 5 homeworks. I don't recommend, trying to go back to all of the homework again. That's just too much to look at all of that. But if there are certain topics that you felt uncomfortable about, or if there was a certain assignment that maybe didn't go so well for you, yeah, sure, by all means, go back to those sections and maybe try those problems or some other similar problems again, just as a way of getting a little bit of extra practice. Okay. Finally, just to remind you that there will be about 25% of this exam based on the proofs that you're going to reproduce in the exam itself. The list of the 5 theorems is in the review packet. Guys, I will be grading those more harshly than I would grade a random problem on the test, because you guys know about this in advance. You're supposed to be studying these theorems and learning however many you need to learn to make sure that you've got it covered, no matter which ones I put on the test. So do learn those proofs carefully. If you've got questions about the proofs, stop by my office hours either later tonight or tomorrow evening, or even on Monday morning. But you should expect that I will be nitpicking those a little bit more than just some random other problems on the exam. Okay, just because you kind of, you know it's coming, right? You should be expecting it. You can do the proofs from the class notes. You can use the proofs from the book, whatever you prefer. Just be careful that if you use some other proof that's like an outside type of proof that maybe wasn't exactly what we did, you might just want to make sure if there's any doubts about certain like statements in those other sources, whether those are things you need to prove or not. If you have any doubts about that kind of thing, you should definitely come check it with me. Okay, and I'll be glad to do that. But yeah, I basically want you to learn some of the important results from the class. And I also want to make this test a little less stressful. You're going to come in on Monday and there's going to be 25% of it that you're already, you know what's going on. You've studied it perfectly, hopefully. I'm assuming you are. So that's the plan, to kind of give you guys some confidence and also to review some important results from the class. So, okay, I think that's my little spiel. I feel like I repeated what I said in the first review session, but are there any questions? Maybe I jogged somebody's thoughts about something they want to ask me about the exam structure or studying for it or anything like that. Okay, well, maybe not. That's fine. If you think of things later, just go ahead and ask me later on. That's totally okay as well. We are going to spend the rest of the time that we're going to be together here in this review just doing practice problems. That's what I like to do. And I mentioned last night that it's a good idea to kind of jump around, do different topics. Don't necessarily assume that everything's going to be directly in order from chapter 2, chapter 3, chapter 4, chapter 5. Things do jump around a little bit. There are connections between the different things that we've done. And so it's good for us to practice that now also, so that when you get to the test on Monday, you've seen some situations where things are kind of coming out of different places and in different orders, so that you're kind of a little bit trained for that. So I am going to throw some problems up here. I'm sorry, I'm just looking on my screen now. Started with this. Oops, there we go. Here it comes. Yeah, so I'm going to throw a problem up on the board from an old exam that I gave. And I'm going to start numbering these examples where we left off last night. Okay, so hopefully that won't be too confusing. Last night we did 7 practice problems. So I'm going to start right now with number 8. Okay. So here is what I'm going to call problem number 8. And what it says is find an integer x such that 1002 times x is congruent to 1 in mod 1333. Okay. And I'm going to give you a hint here, and this is actually off of an old exam of mine, so I know I've asked this question before. The hint is going to be that 1333 actually factors into primes as 31 times 43. Okay, so we'll just go ahead and take that for granted. Okay, so find an integer x such that that equation is true. All right. Does anybody have a suggestion how to maybe start this? By the way, I have my chat window open if you want to use the chat, or you're also welcome to, of course, just use your microphone. But I'd like to make this interactive. We're not in a hurry here, guys. This isn't like a lecture where I have to like cover a certain amount of stuff. So I'm going to just take it at your pace and at the pace of the group here. So let's get some feedback. Brianna's got an idea in the chat, which is to use the separate mods, the mod 31 and the mod 43. Guys, as a general rule of thumb, the smaller the mods, the better. So I don't really like having mod 1333 here. Instead, what we can try to do is work with mod 31 and mod 43 separately. And that's because one of the most important results that we've learned in these first 5 or 6 weeks of this class is the Chinese remainder theorem. And that is what will allow us to take information about x in mod 31 and information about x in mod 43 and paste it together into information about x in mod 1333. Okay, so I like Brianna's idea. Let's do that. So we consider 1002 x congruent to 1 in mod 31, and also 1002 x congruent to 1 in mod 43. We're just going to do them separately. In terms of mod 31, all right, that's a prime number. Is there something we maybe should do with the first equation at this point? Any brave souls out there? I know this Zoom thing is so awkward, but you're more than welcome to use your microphone if you want to. You know, in mod 31, you should never have to look at a number that's bigger than 31, right? Because after all, the numbers are all congruent, that there's a complete residue class system consisting of the numbers from 0 to 31. So I would recommend that we get rid of 1002, okay? And to do that, so let me write it down here so I have enough room to focus on it. What we really need to do is use the division algorithm. Yeah, so I'm going to take 1002 and divide it by 31. So I might have to have a little scratch paper over here. Remember, guys, no calculators on this exam. So we're going to do everything by hand. And so I'm just doing the quick arithmetic here. So I'm actually coming up with a remainder of 8, which I don't know if that's right. Let's see, is that right? 72. Oh, no, that's not right. That's not right. I knew something was wrong. 31 times 2 is 62. Okay, sorry. So we get a remainder of 10, which is actually what Brianna has in the chat, right? So in mod 31, 1002 is the same as 10. So we can change this to 10x congruent to 1 mod 31. Okay? Now that's a linear congruence that we need to solve for x. Does anybody have an idea how we could solve for x right here?
Can we choose x to be -3?
Yeah, remember guys, you can use negatives to help you out. If you don't see off the top of your head a good choice, for x here, we can always basically find the inverse for 10 in mod 31 by using the Euclidean algorithm forward and backward. In other words, we can multiply this congruence through by the same number on both sides to eliminate the 10. We could do that. But in this case, you might just happen to know that 10 times 3 is 30, and 30 is almost the same as what your mod is. So actually, if you multiply this congruence through by -3, you'll get -30 times x, and -30 is the same as +1. So just by inspection, we can take this inverse to be equal to -3. Now, you guys should not be counting on doing things by inspection. Like I would guess that the numbers that I will give you most of the time on the test will be big enough that you actually have to know how to do the steps, right? How to do the Euclidean algorithm forwards and backwards. So try not to lean too much as a crutch on just your, getting lucky with the numbers, because I try very hard not to let that happen very often if I can. But in this case, we can multiply by 3 or by -3. And that'll give me x congruent to -3 mod 31. Okay, and so that's one piece of information about x. We know what it is congruent to in mod 31. -3, of course, is the same as 28, but it doesn't matter. At this moment, it doesn't matter which expression for -3 we use. We can just use -3. It's a small number. Okay, let's look at the other congruence now. We're going to do the same thing. We're going to take 1002 times x congruent to 1 in mod 43. And I'm going to, maybe I'll come over here and do my scratch work in the same part of my board over here. Let's take 1002 and divide it by 43 this time. Let's see if I can do a little better with that. 1002 divided by 43 goes in there, 43 goes into 100 2 times, leaving me 86. And then we bring down the 2, so we have 142. That's going to go into 43 3 times. And we bring down 129, and that leaves us with the remainder of 13 this time. Okay, so 1002 in the world of mod 43 is the same as 13. So this is our new equation right here. I mentioned this last night, and I just want to repeat myself one more time, guys. If you make a numerical mistake over here, let's say you just divide these numbers incorrectly, because again, we're not doing calculators for this test. It's too easy to get too many of the answers just from the calculator. So if you make a mistake, but you carry out the process correctly and you go through the motions of everything and you come up with an answer that's wrong, but it's based on correct process, and you have just some little tiny mistake over here, you're going to get basically full credit. Like, I'm not going to take off much points when you're making mistakes that aren't really math 430 mistakes, right? Yes, in a perfect world, we would never make mistakes with addition, subtraction, multiplication, and division that you learned many years ago. But hey, we're all human. I just made a mistake a minute ago with that previous calculation. It does happen. So don't let that throw off your test or ruin your day. If you feel confident that you're doing the process correctly, but maybe you feel shaky about the numbers, I encourage you to not just erase everything and start over, or just to skip scanning something. You should scan what you have, because there's probably a lot of partial credit there. And a lot of times who does well on a test isn't necessarily, always the person who knows the most stuff. It's sometimes just who was best at communicating, putting their material forward on the paper for me to read. And even if it has a mistake in it, if it's a minor mistake, it's not going to cost you very much. Okay, so just wanted to reiterate that. Now this time, I don't know if it's as obvious how we can get rid of this 13 here. So in mod 43, we're looking for something to multiply 13 by to cancel it. So let's say we don't see, maybe some of you have figured it out, but if you didn't figure it out, you're just simply going to go through the Euclidean algorithm. So 43 is equal to 3 times 13 plus 4. Then we take the 13, and that goes into 4 3 times with a remainder of 1. So working backwards, 1 is equal to 13 minus 3 times 4. Put a little dot here, it's a multiplication. And now I'm going to replace the 4. So I'm going to come over here. This is going to be 4 equals 43 minus 3 times 13. So that actually comes out to be 10 factors of 13 minus 3 factors of 43. Okay, so that is still equal to 1 if I did it all correctly. And in mod 43, the second part just goes away. And the inverse of 13 is just 10. And Sergio has that in the chat. So 10 times 13 is 1 in mod 43. So let's multiply through by 10. So I'm going to multiply by 10. Let me see if I can squeeze this over here. X will be congruent to 10 mod 43. It's a little bit tight, but I'm hoping that that's legible. X congruent to 10 in mod 43. Okay, so we now know, let me summarize what we have. We have X is congruent to -3 mod 31, and X is congruent to 10 in mod 43. Okay, how do we solve for X from here? Chinese remainder theorem, exactly. We have a system of congruences. The mods are relatively prime. We only have 2 of them here, so it's not so bad. And so we can just use the CRT, right? So we have A1 is equal to -3, A2 is equal to 10. Those are just these 2 numbers here. The big N1 is actually 43, and the big N2 is 31. Okay, and then to get the y1, we have capital N1, which is 43 times y1, congruent to 1 mod 31. So we have to solve this little equation right here for y1. In mod 31, I can reduce 43 down to 12, right? So let's do that because I'd rather use a smaller number. So 12 times y1. Congruent to 1 mod 31. Oh boy, so we're kind of in a similar situation to before. We have to solve this congruence. It takes a little while to do. I was looking this up on my old exam. This was like a 15-point problem. Like it's a pretty substantial problem, right? There's a lot to do here on one of these. So to solve for y1, now I've got to run my, my Euclidean algorithm. So I take 31. Let me just go ahead and do it here. If I take 31 and I divide it into 12, it goes 2 times with a remainder of 7. 12 divides into 7 1 time with a remainder of 5. 7 divides into 5 1 time with a remainder of 2. 5 divides into 2 times with a remainder of 1. Wow, that's 4 steps that we now have to run backwards. I think I think I might just tell you what the answer is here, just because it's going to take a little time to run this thing backwards, and I don't know that everybody needs to see me do that. If I should show it, you guys should let me know. But when you run this backwards, you're going to end up getting that y1 is congruent to 13, not 31. So in other words, we just put y1 equals to 13 here. I can show those details if you need me to, but basically you just start with 1 and you run the algorithm backwards. You do have to go through 4 steps very carefully, but you should get 13 for y1. I'm just looking at my solutions to see what the answer was supposed to be. Okay, and then the second one, let's see, over here for y2, on that one we have 31 y2 congruent to 1 mod 43. And so again, we have to solve this linear congruence. And again, if you don't mind, I will just save the headache of that. If everybody's comfortable with this, I will just tell you that y2 comes out, I actually used a negative number as it turns out, negative 18. So we have to run that Euclidean algorithm again on that to come up with the solution there. So y2 is negative 18. Okay, so we have all of these pieces of information, and so then x is just a1, n1, y1 plus a2, n2, y2. So negative 3 times 43 times 13 plus 10 times 31 times negative 18. And that comes out to negative 7,257. This is, of course, in mod 1333. This is another one of those things. I should just say a quick word about this. You know, doing this calculation is like going to take about 30 seconds or more, I think. It's going to take like a little bit of, if you're doing it by hand, it's going to take a little bit of time. Don't spend too much time on it, because if you came up with the wrong number here, but I can see the expression here, I may not even take off any points. Or if I do take off, I would take off maybe 1 point at the most. Okay, so try to not get bogged down. Part of succeeding on the exam is knowing where to spend your time. And you should be spending your time focusing on demonstrating the stuff from chapters 2 through 5 of our book. And that does not include doing hand calculations of things like this. So if you came up with the wrong number down here, I would totally forgive that. It's not a big deal to me. Some people might wonder, well, could I just leave it like this? Would it be okay to just leave it and not even bother to work anything out? The problem with that is, well, what if I ask you for the smallest positive integer x? Well, if you leave it like this, you can tell that this is not positive, but you don't know exactly how negative it is, and you don't know like how many multiples of 1333 you would need to add to make it become a positive integer. So it is important sometimes to be able to simplify these expressions, but in terms of getting credit or partial credit for what you've done up to this point, this is great, and I would be delighted to see it on your paper, but it may just not be good enough to then help you come up with the answer. In this case, find an integer x that works. I couldn't really argue with you if you said, here's my integer x, okay? Because that does work. It just hasn't been, simplified basically. All right, so, use your judgment on this. I'm going to be there, obviously, on Monday. If you come up to a point on the test, you're like, gee, I wonder whether I need to do something else with this number, you can ask me in the chat. I will certainly be there, and I'll do my best to answer those kinds of questions. I'm also going to do my best to write a test where we don't have a lot of these issues of, ooh, gee, can I leave it in this form or do I need to change it? I'm going to try to write questions that sort of force the answer to go into a certain format and into a certain direction. That not to make it harder for you, but just to make it more clear what exactly we're looking for. So that's the way that I'm hoping that it will come out. Are there any questions on this example? We spent a fair bit of time on this one. This is putting a lot of things together. We did a couple problems like this one last night as well. The more times you're seeing me do these kinds of things with Chinese remainder theorem and Euclidean algorithm and so on, right? The more emphasis you could expect that I'm gonna put on it. I'm definitely gonna be. You should definitely be expecting on Monday's test to be asked to do some of this kind of thing here. The numbers will obviously be different, but this type of problem would certainly be something to look at, okay? And certainly expect you to be able to do. Last night, I think we looked at the number 3 to the 999 million power, and we reduced it mod 168. So that was another problem where we took 168 and we prime factorized it, and we solved it in mod 3, we solved it in mod 7, and we solved it in mod 8. We broke it down into the separate mods. So it's the strategy, which is important. That is the same. When you have a mod that is not prime, not a bad idea to try your best to break that mod into separate primes so that you can use the Chinese remainder theorem. Okay, let's go on to another example. I'm going to maybe do one more sort of computational problem here, and then we are also going to do some theoretical examples tonight too. Just like I did last night, I'm kind of doing some of both. Okay, so let's do one more that's just kind of a straight calculation here. So this is number 9. Find all solutions to the following here. I'm going to give you a system again. X is congruent to 5 mod 8. And 5x is congruent to 55 mod 90. Okay. So this is a system of just 2 equations this time. And we want to solve for x. Any thoughts on where to start on this system? How should we maybe start working on this system?
The second congruence, we can definitely divide up the whole thing by 5 to make it simpler.
Okay, I like that idea, Brian. Thank you. Yes, because there's a factor of 5 everywhere. Guys, remember that linear congruences do not always have solutions. Remember, for this linear congruence, you have to take the GCD of 5 with 90, which happens to be 5, and it has to divide the other side of the congruence, in this case 55. If it doesn't, then there's no solutions. And if there's no solutions to this congruence, then the whole thing is game over, basically, right? So it's good to focus on this second congruence first. It does have solutions. And I think personally the best way to work with the second congruence is exactly what Brian suggested, which is to change the mod by dividing through by basically the GCD of the 5, the 55, and the 90, which is 5. So I'm going to just replace the second congruence with a smaller one, which is x congruent to 11 mod 18. Just divide everything through by 5. Okay? So now we have a little bit easier system to work with. Any thoughts on where to go from here?
The two mods are not relatively prime, so you got to use that other theorem.
Good observation, Tuan. Yes, exactly. The mods are 8 and 18. Since those are not relatively prime, we cannot use the Chinese remainder theorem here. Okay, so make sure you're clear about that. The Chinese remainder theorem requires all of the moduli to be pairwise relatively prime. So in this case, that's not the case. So what we can do is use the sort of the alternative approach for a system of congruences, in particular two congruences, where the mods are not relatively prime. First of all, again, the system may not have a solution. What we have to do is take, to test for whether there's a solution at all, the question is, does the GCD of the two mods divide A minus B? And you can see that the greatest common divisor of 8 with 18 is just 2. So this is what I usually call D. D is equal to 2 here. And of course, that does divide -6. So this system does have solutions. And so we can start working on the solution. Actually, sorry, let me clarify. There's a solution to the system. It's unique modulo the LCM of 8 with 18. Okay, so we're going to try to discover this unique solution. So let me just remind you that there's a bunch of variables here that we need to write down. There's an A and a B, which are just the right-hand side of the two congruences. That would be the 5 and the 11. And then there's an N and an M, which are just the respective mods. You really have to be careful on this, guys. And honestly, we didn't get a lot of practice on this in the homework. That's why I did one of these last night, and I'm doing another one tonight, because I do intend to put this on the test. So be very diligent in keeping straight which variables go where. So the A is 5, the B is 11, the N is 8, the M is 18. Then we have, what else do we need? We need D. D is the greatest common divisor of 8 and 18, which is 2. When we presented this in class, I used a variable T. T represents A minus B over D. So that's -6 over 2, which in this case would be -3. And then there are just two other variables, which are R and S. And I'm just going to remind you that basically what you have to do is write the GCD of 8 and 18 as a linear combination of 8 and 18. This is one of the things we definitely learned how to do. So we can write the GCD in terms of those two numbers. Make sure you put the R and the S with the correct number, right? The R goes with N, N was 8. And the S goes with M, which was 18 in this example, okay? You can obviously take this thing and divide it through by 2 all the way across. That's perfectly fine. No reason not to do that. And actually, we can run the Euclidean algorithm on 4 and 9, but I actually can see the answer already that would work, or an answer that would work. Remember, this is not a unique equation, but all you need is some valid solution. And I can just tell with small numbers that I can take R to be -2 and S to be 1. That's what will come out, I think, if you just do the Euclidean algorithm on this one. It's not that hard to come up with these two values. So let's put those in over here, -2 and 1. And next, what I hope everybody has on a flashcard somewhere is the formula for the solution to the system. We call it X. Well, it is X, as you can see. And there's two different ways to figure it out. It's A minus NRT, or it's B plus MST. Okay. This is one way to, I don't know how you guys will remember it. B plus and A minus are right next to each other on your grade scale. That could help you. You're always putting the minus with the A and the plus goes with the B on this one. Okay, so we can use either of these two formulas. Let me just use the one on the top. This is going to be 5 minus, let's see, n was 8, r was -2, and t was -3. So that's 5 minus 48, which is -43. Okay? And, you know, it's never a bad idea to check your answer if you can. Just plugging -43 into the two congruences to make sure that that works is you know, always, that's always a good idea. So we certainly can come up with this. Now, remember, this is a unique solution modulo. This is unique modulo the LCM of 8 with 18. Remember that the LCM of two numbers is simply the product of those two numbers divided by the greatest common divisor. So in this case, that would just be 72. And so essentially, it says find all solutions. That's the question, find all of the solutions. So you would basically say that your final answer is any x that's congruent to -43 in mod 72. This is the answer. You cannot write down all of the solutions literally because there would be infinitely many of them. We can add and subtract 72 all day long, forever and ever, and come up with more and more and more solutions. So you can't list every solution here, but you can express the congruence expression of the solution in just one line right here. My question, you know, on the test, I might ask you, well, give me the 3 smallest positive solutions. So you then have to take this one and add 72 to it, do that 3 times and come up with 3 solutions. Okay, so just make sure you read the question really carefully of what's being asked for. And that'll help keep you out of any trouble there. Okay. By the way, you can leave the second congruence mod 90 if you want to, but it's not a good idea. Because in mod 90, there will be 5 incongruent solutions to the second congruence alone. You would have to take each of those 5 and pair it with the first equation and do basically this process 5 times. You don't want to do that. Not on this exam when you've got an hour and 15 minutes, right? That's way too much time and effort to come up with all of the 5 incongruent solutions. So it's much better to do exactly what Brian suggested. We divided through by 5 in the first place on that second congruence, just to cut down the numbers and also cut down the number of cases of how many solutions you're going to have. All right. Any questions on that example, guys? No? Okay, great. Let me see. I'm looking to see what I want to do next, solutions wise. Yeah, let me give you this one. Going to kind of keep jumping around a little bit. So this is number 10. And what it says is find all solutions if any to the following equation. X to the fourth plus 5x cubed plus 4x squared minus 4x minus 3 congruent to 0 mod 52. Okay. This one you might feel is a little out of left field. It's not a linear congruence at all. This is a quartic polynomial, basically. It's a polynomial of degree 4. You might say, oh, gosh, we haven't done any polynomials of degree 4. We've mostly been looking at linear congruences and systems of linear congruences. So the question is, how could this be a fair question? Like, why is this reasonable for me to ask you this question right now? Maybe as we start to think about it, it'll become a little more clear what we can do here. Does anybody have any thoughts about what we could do for this? Brianna mentions in the chat the theorem 5.5. This one has to do with, remember theorem 5.5, x squared plus 1 congruent to 0 mod p. So a couple of questions about that. First of all, we don't have x squared here. We have like some huge 4th degree thing. And also the modulus is not a prime. So it's certainly not going to be directly in terms of theorem 5.5. However, it does give me the idea of factoring 52. Always a good idea to think about factoring the modulus. In this case, when you factor 52, let's see, what is that going to give me? That's going to be, 2 squared, which is 4 times 13. So if this was like one of our earlier problems, what we would have done at this point is just say, let's look at it in mod 4 and let's look at it in mod 13, right? This is so often what we do. And then normally we would use the Chinese remainder theorem to sort of paste the solution back into mod 52 again. So let's try that. Let's try that. So let's consider x to the fourth plus 5x cubed plus 4x squared minus 4x minus 3 congruent to 0. Let's just look at it in mod 4 for a moment. Let's just look at it in mod 4. I think this is probably a reasonable starting point. Mod 4 is not such a terribly intimidating modulus. For example, if you're in mod 4, what could you do to make this a little easier on yourself already?
You can start modding out the coefficients.
Yeah, the coefficients of this polynomial in mod 4 can be reduced, right? So this would be x to the fourth plus x cubed, and then just minus 3, which I can also write as plus 1. Right? So in other words, in mod 4, our polynomial kind of collapses into something that's a lot more manageable, right? It's just got these 3 terms. So we're just taking the coefficients and we're just dropping them down between, 0 and 3, basically. Now, I should point out that, if there's a solution to this first congruence, if 52 divides this expression up here, then 4 has to divide that expression too. Of division. So 4 divides 52, which divides our polynomial. So that means in particular that 4 has to divide this. So this is good. We've got it basically expressed using a modular equation, a congruence. But it's still not linear. I want to also point out, guys, we cannot really use Fermat's little theorem here either. I know we might be looking at these exponents, wishing we could like pull them down using, you know, so x to the p minus 1 is congruent to 1 in mod p. But this is not a prime. Maybe when we look at mod 13, we could get some benefit from that, but we're not going to get it in mod 4. The other thing I want to remind you guys, this is like the classic mistake 101 in number theory, which is I see people trying to just reduce the exponents in mod 4. That we cannot do. So x to the 4, in fact, I think I had some homework where you did an example. You showed that, you know, just because A is congruent to B in mod n doesn't mean that x to the A is congruent to x to the B. So the powers cannot be, like you can't really reduce these powers unless you're using Fermat's little theorem, right? So Sergio, I see you wrote that in the chat, but we cannot use Fermat's little theorem here because we don't have a prime modulus. So there's no Fermat's little theorem. There's no way of simplifying this any further. So what else could we do?
Humberto says we gotta brute force it.
Brute force it. You know, in mod 4, brute force doesn't sound that bad to me. In mod 4, there's only 4 numbers: 0, 1, 2, and 3. Or actually, even better than that, 0, 1, 2, and -1. You're allowed to use negatives if you just try them. So 0 to the 4th plus 0 cubed plus 1, that doesn't work. These are all in mod 4. 1 to the 4th plus 1 cubed plus 1, that doesn't work. 2 to the 4th plus 2 cubed plus 1, you got to work this out a little bit. 16 plus 8 plus 1 is 25. That doesn't work. And finally, I'm just going to use -1 to the 4th plus -1 cubed plus 1 in mod 4. That doesn't work. None of them work. None of them work. There's no x's that satisfy this congruence, which means there are no solutions to the original congruence. I don't even have to work on mod 13. We can just stay away from that one completely. We don't even have any solutions in mod 4. We just try to plug everything in. Nothing works, right? So the answer here is no solutions. There are no solutions to this one. Small mods are your friend, right? They allow you to get away with stuff like this, where you just trial and error plug these numbers in, okay? So take advantage of that. It's just it's, you know, you're not going to get this exact question on the exam Monday, but you might get something that uses this idea that with a very small mod, we can actually just run through every case and see what happens. So you know, that's what I want you to kind of take away from this. Questions here? Yeah, so there's really no, you think about using some theorems, you know, where's Fermat's little theorem? Where's, you know, Chinese remainder theorem? It's just not going to help you with this one. Okay, we don't have much we can say. All right, let me go back to my screen that I'm looking at here to come up with what I want to do next. I just have to find where this is. Yeah, okay, so I've got another problem for you. So let me just do a couple like slightly more theoretical examples. I did some last night, and I think it'd be good to just show you a few more tonight, just to see some things here. So this is number 11. Let's do a proof, okay? So these are obviously going to be proofs. If A is odd, then 32 divides the quantity a squared plus 3 times a squared plus 7. Okay. This isn't anything too crazy. Probably got some ideas here. Any thoughts on what I might want to do with this one? I think this is off of one of my old exams as well, so I must have thought it was reasonable then.
Can we plug in for I think it's 2k plus 1?
Okay, great. Yeah, if it's an odd number, we can write it as 2k plus 1 for some integer, okay? So let's start that way. So for the solution, let's just write a equals 2k plus 1. This is going to be for some integer k. We take an integer k, we're going to write a like that. And then what would you like me to do with that?
Yeah, just plug it in into the a squared plus 3 and then the a squared plus 7.
Okay, good. Let's look at the a squared plus 3 and the a squared plus 7, and we'll replace it with this. Okay, let's just see what happens with that. So then what we're going to get here is a squared plus 3 times a squared plus 7. This is going to be 2k plus 1 squared plus 3 times 2k plus 1 squared plus 7. And we just have to be very careful when we multiply this out. We don't want to mess this up. So otherwise, we're not going to get the conclusion that we want. So let me work this out kind of carefully. When I square out the 2k plus 1, I should get 4k squared plus 4k plus 1. And then there's a plus 3 there as well. Second term, very similar, 4k squared plus 4k plus 1 plus 7. And let me just combine some things together here. We have 4k squared plus 4k plus 4 times 4k squared plus 4k plus 8. Okay, so this is literally just multiplying it out. And what you probably notice already is that both of the factors here have 4s that can be pulled out, right? So I can actually pull a 4 out of here and out of here, which will give me 16. It's going to leave me k squared plus k plus 1 and k squared plus k plus 2. Those two numbers right there. So we factor the thing out like that. We're trying to show that what we have is a multiple of 32. And we see a 16 already right here, but that's not quite 32. Does anybody see something as to how I'm going to now get 32 to divide this expression here?
Just group up your k to the power 2 plus k plus 1, so you have 2 times that, and then you can just multiply that by 16. So
I'm sorry, could you say that one more time?
so you have 2k, so you have k squared plus k plus 1 2 times, so that's 2 times k squared plus k plus 1, and then you have the 16 on the outside, so you just, so I'll write it down.
I don't see what you mean k squared plus k plus 1 2 times.
So, oh wait, never mind. I just realized that the other one had 2. All right,
Yeah,
never
this
mind.
is a plus 2 over here.
Yeah, I didn't realize that.
Okay, no worries. That happens to me all the time. Does somebody else want to jump in here? Is there a way to kind of get 32 to divide this whole thing?
Is it something having to do with like we have to consider the cases of k, like if k is odd or if k is even? Like
We could certainly do it that way. That would work if we wanted to look. So the thing is, if k is even, then you might notice that this second factor would be even. So we would get a factor of 2 out of there, which we could combine with the 16 to make 32. On the other hand, if k was odd, then, well, actually, this would be an odd plus an odd, which would be even, and you add 2 to that, it's still even. So actually, k squared plus k plus 2 is always even. That's really the point. Because k, whether k is odd or even, when you add 2 odds, you get an even, and when you add 2 evens, you get an even. So I'm just going to note that we actually don't need to do it as 2 cases here. We can just simply say k squared plus k plus 2 is always even. Say it equals 2m. So we can write it as 2m. And it's always good to quantify your variables when you're bringing them into the problem. So there's some integer m such that we have a 2m there. And so now we can just say that a squared plus 3 times a squared plus 7 is 16 times k squared plus k plus 1 times 2m, which is, I don't know, 32L for some L in the integers. And that's basically the end of the proof. You've got it as a multiple of 32 here. The other thing I want you to notice about this is that there's another way we could have argued this a little bit. You see these two numbers here? How far apart are they? 1, right? If you have 2 consecutive integers, guys, one of them has to be even. So if you don't want to have to think about whether, which of these terms is odd or even, you could just say, look, out of those 2 consecutive integers, at least one of them can be written as 2m, and then more or less write up the same thing. Okay, so that's just another way to kind of get the point across. Does this make sense? Okay, so this wouldn't be too bad if I put this on the test. I'm hoping everybody's feeling like, yeah, I could do these problems, and if you got asked something like this in the future, that you'd have some ideas what to do with it. Okay, let's do another example. Can I erase? Everybody got this one written down mostly? Okay, fantastic. Let me come back up to the top again. I will be sending you guys the link to this recording also later on this evening as soon as this thing compiles. So if you want to watch any of this again, or if you just happen to miss any of the notes, they will be available to you. Okay, let's do number 12, I guess it is. And here is what it's going to say. An integer is square free. So I'm actually going to make up a definition in the middle of this problem, okay? It is square free if it is not divisible by the square of any integer that's greater than 1. Okay, so there, you cannot have 4 as a divisor, or 9, or 25, or anything like that. Okay, so that's just a definition. That's obviously, we didn't cover this in the class directly, although we're going to see that square-free integers are very nice in many ways, and they are going to play a role later on in the semester and some of the things we're going to do with perfect numbers and so on. But what I would like to do right now is just take that definition and prove that every integer n, let's make n greater than 1 just to keep it from being trivial. Every integer n greater than 1 can be expressed can be expressed in the form n equals s times t squared, where s is square free. And of course, t is an integer. Okay, so this one took a little bit more time to write it down. So let me just take a breath here and let people kind of soak this one up. So this is a little theoretical problem. I mentioned last night that on the test, there will be several theoretical problems, but I probably will not force you into solving, like, I'll give you some choices somehow. I'll either just say, do 3 out of these 5, or I might say something like, I'm just gonna drop your lowest one, whichever one that happens to be. I'll try to set something up like that so that you have a sort of a get out of jail free card that you can play on something. You happen to, it just doesn't hit you during the exam. You're like, I don't want to think about this. You're going to have to think about a lot of things, but I'm probably going to set up some system where you won't have to do everything on the test. But this would be more of a theoretical question. The other thing I might mention is if you're not quite sure what's going on a certain problem, this one's a little bit, we have a definition in here and it's a little weird. One thing you might think about doing is just try it out on a number. Like this says every integer should be expressible in this form. So one way to kind of understand the problem a little bit might be to just take an example. Let's just do that just to see if we can get the idea here. Let me just pick a number that's kind of mid-range. I don't want to pick it too big or too small. Let's just pick a number like 90. And let's see if we can figure out how to write it in this form right here. Okay. So when you think about 90, of course, what do you think you're probably going to want to do first if you're trying to express it in this form that we're talking about here?
You probably want to divide it by the square, the t, I guess. So here, the 9.
I see the perfect square, which is the 9. So we know that there's a factor of 9 in here. And so we could like divide by the 9 and then see what's left over. Is there sort of a way of kind of doing something similar to that, getting the same information, but without having to do division and kind of creating
Factor
fractions?
90.
Say again?
Factor 90.
Yeah, how about let's just do the factorization of 90. And what allows us to do the prime factorization of a number? What's the result that's related to?
Fundamental theorem of arithmetic.
That's the one. Yep, that's the one. The fundamental theorem of arithmetic. It's one of the proofs in the list of proofs for the exam, and it's a very, very big theorem. It's another one of these really important results. It basically says that every number is uniquely factorable as a product of powers of primes. So in this case, you can very quickly figure out that what this factorization is. Just to see an example on the board, this would be an example: 2 times 3 squared times 5. Okay. Yeah, Twan's remembering that I mentioned that this one might come up at graduation. So make sure you study before you go to your graduation, especially if I'm going to be there in the front row. Anyway, let's see. And the CR, another big one. We've got some big theorems here, guys. There's no question about it. So do you see how we can do this? A square-free number should not be divisible by any square. It just means there'll be no square powers in this number. So you could actually think of this as 2 times 5 because there's no squares there. and then 3 squared. So this would be your s, and then this would be your t squared, like that. Okay, something like that. That could be an example. Now, if I jacked this up to, let's say I put this up to 270, which would be 2 times 3 cubed times 5. So in this case, your t squared is still just 3 squared. So you actually have to take one of the 3's and put it into the s part. So because this t squared has to be a squared right here. There's no other choice for that one. But you can take an odd factor of 3 and put it in with the s part. What if I go up by another factor of 3? What if I had 810? So now that's going to be 2 times 3 to the 4th times 5. Well, now on this one, again, I can go back to just the 2 and the 5 as being part of the s, and then I can take 3 to the 4th and write it as 9 squared this time. So the integer t does not have to be a prime, it just has to be an integer. So we're allowed to use a 9 on this, on the factorization that we're describing right here. So this just to show a couple of examples to kind of get the idea like what this problem is really doing. So now I'm going to try to talk us through the proof. Okay. Hopefully the examples kind of help us understand what's going on, right? I bet we have a pretty good idea how to start the proof, because in all of those examples, the very first thing we did was prime factorize the number using the fundamental theorem of arithmetic. So I would actually argue that that's a good thing to just do in the general proof here. So let's just do that. Let's using the fundamental theorem of arithmetic, let's just write n. I think I'm going to try and use the same notation that's in the fundamental theorem of arithmetic. P1 to the K1 times P2 to the K2 all the way up to PR to the KR, where the PI's are distinct primes and the K sub i's, well, those are all the exponents of those primes. Those are just going to be at least 1. So we know that every integer has this kind of a representation. It's the fundamental theorem of arithmetic. And so we're actually going back to sort of earlier in the semester, right? We did this kind of first or second week. Now, what really seems to matter on this factorization, what really seems to matter is whether the K sub i's are even or odd, right? If the K sub i's are even, then that basically means that that factor is already a square. We can put it into that square piece. But if though any of those K sub i's are odd, then we actually have to pull one of those prime occurrences out and put it in with the square free part, and then keep the rest of it into the perfect square piece. So this is the idea, guys. We have to look at these exponents, these K sub i's, and we need to know, are they even or odd? And in fact, what we can do is we can actually get more precise than that. What I can do is for each K sub I, I'm going to write K sub I is equal to 2Q sub I plus R sub I, where R sub I is 0 or 1. right? This is by the division algorithm. So by the division algorithm, I can actually take those exponents and split them like that. So I can just take them and divide them by 2. We're going to get a quotient and a remainder in each of these cases. Okay. Now, if the R sub I is 0, that would just mean that K sub I is even. And if R sub I was equal to 1, that would just mean that K sub I was odd. Of course, we could have some of each. But let's just assume that we've arranged these primes in a certain order so that the even ones are kind of together and the odd ones are kind of together. So I'm just going to assume, without loss of generality, I'm going to assume that R sub, let's see, R sub 1, R sub 2, up to R sub t, that all of those are equal to 0. And then the ones after that, R sub t plus 1, R sub t plus 2, and so on, all the way up to R sub, oh my gosh, this is horrible, R sub R. Yeah, I guess that's what we have. Those are all equal to 1. This is not the world's best notation on my part, so I apologize for that. Okay. So if I do that, and if the notation isn't too crazy, I think we can now write our number in this form. I think we can do it, right? We can do it. Let me show you how. So then n is equal to, for all of these primes that had an odd number of occurrences, right? The exponent was odd. We're going to grab one of those for each one of those. So I'm going to put pt plus 1 ... up to pr right there. Those are just all of the primes that occurred an odd number of times. And then I'm going to basically grab everything else and try to write it as a perfect square up here. And how am I going to be able to do that? Well, essentially what I have to do, I claim, basically, I've pulled out the R sub i's from the t plus 1 through r term. So we're no longer looking at that so much. We have exactly 2 qi of each of the prime factors that are still left. And we're going to be squaring them here. So I'm literally going to take each one of my primes, P1, P2, and so on, all the way up to PR, to the QR, and I'm just going to write all of that in where the T belongs. So if you were to multiply that out and look at your exponents, the exponent of P1 would be 2Q1, which is K1. The exponent of P2 would be 2Q2, which is K2. It's exactly what it's supposed to be, right? And so on and so forth. What about the last prime, P sub R? Well, for the last prime, I have 2QR plus one more copy, right? It's over here in the S piece. So that's 2QR plus 1, but that's exactly KR. Because remember, the R, we're assuming that R sub R is 1. So there is an extra factor of that particular prime that we have to write down. Okay, so that's kind of the idea of how something like this one would go. It's a little tricky, but again, if you just start writing out the fundamental theorem of arithmetic first, I'm going to give you something for doing that. Yeah. And then if you don't totally figure the whole thing out, I know that the notation is a little tricky, but if you have some idea of what to do, I will definitely obviously try to give you some partial credit for it. So just wanted to show you one that was maybe a little a little more challenging application of a very basic theorem, which is the fundamental theorem of arithmetic. Okay. Sorry, I am just looking around on my screen here again. Are there comments here, questions? Does anybody else know that? Do you guys know what else you can do with the fundamental theorem of arithmetic? Like what other kind of, have we seen any other problems where we're using that in this class so far? Pretty sure we had some work on it.
I think we used it for that proof that there's infinitely many primes of the form like 4k plus 3 or something like that.
That was not so much the fundamental theorem of arithmetic. That was more just, we multiplied a bunch of primes together. We created a number that would give us a contradiction, essentially. If there were finitely many primes, then, you know, all of those primes would have to divide that number. And so therefore, you know, you somehow create a contradiction out of that. You end up proving, for example, that one of your primes divide to 1 or something crazy like that. So I don't think that was really the fundamental theorem of arithmetic directly. But there was something that we did use the fundamental theorem of arithmetic to do, a type of problem. And I'm wondering if anybody remembers what it was. No, maybe we need to review this then. I'm going to make up another problem right now. Okay. And this will be easier than the one we just did. So let me make up another example. Grab my eraser here. So let's try this one. I believe we did this. You guys have to correct me if I'm wrong, but I'm almost positive that we did this. This is going to be number 13, I think. Let's prove that the 13th root of 6 is irrational. Does that sound familiar? Yeah,
does, yes.
We've done this kind of problem. So the idea is a rational number is a ratio of 2 integers. So what I do for something like this is I go by way of contradiction. By way of contradiction, let's suppose that the 13th root of 6 is m over n for some integers m and n. So we just start off imagining that it is a fraction. And we immediately want to clear out the fraction though. So I'm going to cross multiply the n to the other side of this equation then. So then what we'll have is m equals the 13th root of 6 times n. And just to make this a number theory problem, we don't want to have anything except integers in here. So I'm going to actually raise both sides to the 13th power. Okay. So then we would get m to the 13th is equal to 6 times n to the 13th. So this is the idea, is to get rid of the radicals and get rid of the fractions. Now we have an equation that fully involves integers. Okay. What you want to do on something like this is we're going to use the uniqueness part of the fundamental theorem of arithmetic. The fundamental theorem of arithmetic says every integer can be factored uniquely as a product of primes. So if you look at this number, we're representing the same number in 2 ways. When you look at it on the left side, every single prime that shows up in M has to show up a multiple of 13 times. Because you're writing down m 13 times on the left side of this equation. So whatever its factorization is, all of its factors have to occur a multiple of 13 times. There's 13 sevens. There's 26 11s, right? There's 13 13s, whatever. It has to be multiples of 13 for each prime factor on the left side. Now on the right side, the same thing has to be true because it's the same number. But what you'll notice is that the prime factors in the n to the 13th, they also come in multiples of 13. And where we get into trouble, guys, is with the 6 right here. Because that produces an extra factor of 2 and an extra factor of 3. So we don't actually have to write out prime factorizations of m and n here. You can do that, but we don't need to. What we can simply do is we can just simply say, note that m to the 13th has k factors of 2 where 13 divides k. So the number of factors of 2 is a multiple of 13. Okay? However, well, let me just say it this way. So similarly, n to the 13th has, I'm going to call it L factors of 2, where 13 divides L. And so thus, 6n cubed has L plus 1 factors of 2. And 13 obviously does not divide L plus 1 because 13 does divide L. So compare the number of factors of 2 on the left side to the number of factors of 2 on the right side. And you can see that, well, k is a multiple of 13. That's on the left side, the number of factors of 2. But the number of factors of 2 on the right side is not a multiple of 13. Okay, so this violates, this contradicts. Okay, so I'll just say since m cubed is equal to 6n cubed, this contradicts the uniqueness in the fundamental theorem. I'm just going to have to abbreviate it here. The fundamental theorem of arithmetic, FT of A. So every prime factor needs to occur the same number of times on the left side as the right side. Renee, did you have a question or a comment?
I just had a comment on you started putting n cubed instead of n to the 13th.
Oh, shoot. You're absolutely right. I like to make mistakes on purpose occasionally just to make sure everybody's paying attention out there. So glad you caught that. This was supposed to be 6n to the 13th, and this is an m to the 13th and an n to the 13th. Did I mess it up anywhere else? No, looks okay. Thank you for catching me. I got screwed up and changed my 13 to a 3. That's my bad. Any other questions on this example, Humberto?
Yeah, why did we choose the factors of 2 again?
Because of the 6. We could have chosen to do this with the factors of 3 instead of 2, but the 6 is what's creating the problem with the balancing of the prime factorizations. So you're going to want to take you're going to want to focus on a prime that is contained in the factorization of the number 6. Either one of those would be fine. That way you get an inconsistency. If you focus on factors of 5 right here, you're not going to get any contradiction because the number of factors of 5 on both sides of the equation can be a multiple of 13 without having any discrepancy between the two sides. So you've got to choose either 2 or 3 for your prime. Does that make sense?
Yeah, it does. So if it was 8, we would choose 2 again, right?
Yeah, if it was an 8, I would choose 2. You know, you basically would, so it's the number that's under the radical is what really ends up driving the choice of what you're going to do. So that's really the number that you need to look, what's the factorization that number has, and then grab one of those primes. Hopefully that's where you're going to get your contradiction out of. Okay, good. These are a couple of good examples of the fundamental theorem of arithmetic here. Any other questions on this topic? We didn't really review this one last night, so I wanted to make sure tonight that I did take a little time for it. Okay, great. Let's do another example. I'm going to come back up to my board here. Just going to do a couple more examples tonight, guys, then we'll probably call it good. We may actually get out of here a little bit early, which wouldn't be the end of the world. I want to actually, what I'm going to do next is I want to make sure I've had a chance to talk about the problems from that one group work that we never actually did, which is group work number 3. So let me throw this question about twin primes on the board real quick. So this is number 14. I'll put the definition up here. So 2 primes, P and Q, are twin primes if the absolute value of P minus Q is equal to 2. Okay, so these are primes that happen to be exactly 2 apart from one another. And let's do a couple of parts here. So this problem is going to have a couple of parts. So for part A of this one, let's prove that if P and Q are twin primes, then what do I want to say here? P times Q plus 1 is a perfect square. So a nice example of this, if I took, you know, just to see an example, if P was 11 and Q was 13, then that's 2 twin primes. Those are primes that are 2 apart. If you calculate P times Q plus 1, you actually will get 144, which happens to be 12 squared. Okay, so it is possible to get the idea just from an example. By the way, guys, examples are useful for figuring things out. If you wrote this down as your solution to this problem, I might give you one mercy point for at least kind of trying to play with it a little bit. But for proofs of things that are true, an example is not really a proof, right? This is just sort of showing one case. It doesn't really prove it. I might give you some statements on the test where there's something that might be a false statement, and I might ask you, give me a counterexample. So that is certainly something I might do. But if I'm asking you to prove something like this kind of thing here, don't just do it. Writing down an example is okay to get the idea if you need to. And maybe I'll give you a point for that if that's all you come up with. But I would much rather see you try to do the general proof. Okay, so let's, now that we've at least seen one example of it, let's try to go to the proof here. Anybody have a thought as to what we might want to do to start off on this?
Can we suppose that P is greater than Q?
Yeah, let's do that. Let's suppose that without loss of generality, let's assume that P is greater than Q. Probably a good idea to do that, just to fix ideas here. And then what could we do next?
We can take our equation towards the absolute value of P minus Q is equal to 2. So we have now that P is equal to 2 plus Q, and then substitute it into PQ plus 1, and then see what we get.
Oh, okay. So you're gonna basically take the absolute value bars away now, since P is assumed to be greater than Q, and then you're gonna just solve this for P. So P is equal to Q plus 2, and then we can feed that into this expression here. Am I doing what you said, Sergio?
Yeah.
Okay, great. So you get something like this. You're just replacing the P with Q plus 2. If I multiply this out, then I'm going to get Q squared plus 2Q plus 1. And that does look familiar. That is actually just Q plus 1 squared. So it is a perfect square. So this certainly works just fine. Sorry, I'm just getting my screen back up here. By the way, this is not the only way to do this. I'm wondering, does anybody else have another thought how we could have done it differently?
Can we assume that since they're twin primes, that P and Q are odd numbers?
They both have to be odd, don't they? That's right. That is exactly right. They both have to be odd if they are 2 apart. And so you can write them. I assume this is where you're going, Brian. You want to write them as like 2K plus 1 and things like that.
Yeah, write it out and then plug that in for our assumption and then see if it works.
That's exactly right. So what you could do is you could write, P is 2K plus 3 and Q is 2K plus 1. K is an integer here. So, you got 2 consecutive odd numbers, right? These would be 2 consecutive odd numbers. And I'll leave it to you guys to check that this also will work out. If you multiply these together and then add 1, you'll be able to factor it out as a perfect square. So that is actually another way to do this problem. It's kind of a slightly different solution. But Sergio had a great idea here too, which is to just, without loss of generality, assume that P is the bigger number, and then you can get rid of the absolute value bars and pretty quickly calculate some things. Okay, let's do another part to this question. Right. Hopefully I'm not erasing too fast, but if I am, the video will be coming. Here it is. So part B, this is right off of group work number 3. So again, if P and Q are twin primes, and then we're going to, and P is greater than 3. Then P plus Q is divisible by 12. Actually, yeah, so sorry, I'm just thinking about something for a second. Yeah, I guess that's okay. I don't know why I specifically said P is greater than 3 instead of P and Q, but it's all right. We'll just take this as it's stated for now. Okay, so we have 2 twin primes, P and Q again, and let's just assume that P and Q are both greater than 3. I'll have to look back at my solution and see whether that matters. But in other words, I mean, I can tell already if P is equal to 3, then Q has to be 5, and 3 plus 5 is not a multiple of 12. So it doesn't work. It doesn't work if 3 is one of your twin primes. That's basically the idea. Let's assume that the smallest of the two numbers is at least 5. So P and Q are both at least 5. So for example, 5 and 7 would be okay, right? 11 and 13 would be okay. So we would be able to get multiples of 12 in this case. Okay. So let's try to prove that P plus Q is divisible by 12. Now, for a number to be divisible by 12, it needs to be divisible by what two numbers?
3 and 4.
Yeah, 3 and 4, because 3 and 4 are relatively prime. And so if we can show that P plus Q is divisible by 3 and by 4, then we're going to be able to say that it's divisible by 12. So this is how we're going to really do this. And the solution kind of follows the approach of what I was just talking about a moment ago, which is, let's assume that P is, well, 2k plus 3 and Q is 2k plus 1. And in this case, I guess we can say that k is an integer that's at least 2, because we're not allowing 3 to be one of our twin primes. So we can write out our two, these are odd numbers, right? And let's just add them up. So then P plus Q is, well, 2k plus 3 plus 2k plus 1 is actually 4k plus 4, right? And that is obviously a multiple of 4 right away. So P plus Q becomes a multiple of 4, which is one of the things we needed to show. We need to show divisibility by both 3 and 4. And I can see from this that P plus Q is divisible by 4. Now, it doesn't look nearly as obvious that, that P plus Q is divisible by 3 right now, to me at least, right? So it's a little bit hard to say what we're going to do. I mean, what we could do here is we could say, look, this is 4 times the quantity k plus 1. And so if I want to show that 3 divides this whole expression, we really need to show that it divides k plus 1. So we need to show now that 3 divides k plus 1. And in other words, let me just phrase that as a congruence. K plus 1 is congruent to 0 mod 3. Or let's just rephrase that one more time. K is congruent to, it's actually going to be 2 in mod 3. We need k to be congruent to 2 in mod 3 in order for 3 to divide k plus 1, which is what we need for it to divide P plus Q. Any ideas how I would show that k is congruent to 2 in mod 3? Because we still need to do that. You know, mod 3 is not very big, right? It's not very big. Every number in mod 3 is either congruent to 0 or 1 or 2. And all we want to do is show that in this setup, that k actually has to be congruent to 2. what's a way that we could do that? Like, I don't want to know the details yet, but just from a strategy point of view, is there a way that we could funnel the conclusion into what we want right here?
Just do testing, just having all the variables, like assume k is congruent to 0, k is congruent to 1, and then so on.
Okay, so we could look at those other cases and try to disprove them, right? One way to prove that k is congruent to 2 would be to show that it's not congruent to 0 or 1, right? If it's not congruent to 0 and it's not congruent to 1, then it would be by sort of default, it would have to be congruent to 2 in mod 3. So the claim is, so this is another strategy, guys, is sort of to do proof by cases, so to speak. Let's prove that k is congruent to 2 mod 3. And the proof is, well, if k is congruent to 0 mod 3, let's try to derive a contradiction, right? Well, what does this mean? This means then k is actually a multiple of 3. So let's call it 3L for some integer L. And in this case, if k is equal to 3L, does anybody see a contradiction? Look at the number p. And imagine if k was equal to 3L.
It would have a factor of 3, and therefore it would not be prime.
You see right here? Exactly. If k was 3L, we could pull a 3 out of it. And that would make p not a prime, right? So if k is equal to 3L, then p, which is 2k plus 3, would become 2 times 3L plus 3. And I'm going to pull out a 3, leaving me with 2L plus 1. And this is so, therefore, p is not prime. Because 2L plus 1 is going to be 2L plus 1 is going to be at least 3. L is going to be at least 1. If L is 0, then that would mean that k is 0. And if k is 0, then look at what your numbers p and q are. They don't work, right? They're not big enough. K was supposed to be at least 2. So if k is at least 2, then L is at least 1, which means your factorization here is not trivial. Okay? So this is a contradiction in this case. So then let's go to the other possibility. If k is congruent to 1 mod 3, well, then I'm just going to write k as 3L plus 1 this time, again, for some integer L. And any thoughts what maybe I'm going to do this time?
Would it just be the exact same thing that we did for k is congruent to 0?
So you want to plug it into the p here?
If it follows the same thing, then yes.
Let's try it. Let's try it. So if we do that, put in p equals 2 times 3L plus 1, and then we have a plus 3 on the end of that. This becomes 6L plus 5 this time. You see, the problem is I can't factor this. I can't pull out a 3 from this one the way I could up here.
But if you plug it in Q, you can.
Okay, let's plug it into the other value, which was Q. Very good, Renee. That's a great idea. So, and then Brian, that was a good idea too. This time we do want to use Q. So Q, which was 2k plus 1, becomes 2 times 3L plus 1, and that is 6L plus 3. And again, I can pull out a 3, and it leaves me with 2L plus 1. And so Q is not prime. And that is a contradiction again. And so basically, after you sort of throw out those cases, then we can conclude the only other possibility that's left is that K is congruent to 2 mod 3. And from there, we actually do manage to get that. That basically does allow us to prove that 3 divides P plus Q. Okay, so hence, the LCM of 3 and 4 also has to divide P plus Q. In other words, 12 has to divide P plus Q. So I'll let you guys jot that down if you like getting these notes kind of exactly right. That's basically the way I would say it. So yeah, the twin primes, when you add them up, you have a multiple of 12. Okay. There is one more part to this, and then that's probably going to bring us just about to the end of 2 more hours of this stuff. So I think I'll do one more part, and then we'll kind of wrap things up. I'll see if there's if anybody's been holding on to any questions out there. I'll give you guys a chance before we wrap this up. Don't forget, I have office hours tonight. I can't remember if I'm starting right away. I might have an hour break first. I can't remember, but I'm going to be going over to my Zoom office hours this evening. If anybody is not exhausted yet or sick of number theory by now, I'm going to be available to keep working for a while. But let's do one more problem about twin primes here. This last one I don't think is so heavy in terms of what we have to write down. So this is part C. It says, find all twin primes whose average, I guess we're going to look at the average of these 2 twin primes, whose average is a perfect square. All twin primes whose average is a perfect square here. So again, we already kind of know how we've been writing this out before. We have P is equal to 2K plus 3, and Q was equal to 2K plus 1. I hope that was the way I did it, where K is an integer. This is consistent, right, with what I was doing earlier, these 2 choices. So the average is just, of course, 2K plus 2. It's just the number right in the middle. Okay, so the average is halfway between those 2 numbers, which is 2K plus 2. Or if we want, we can factor this out as 2 times the quantity, K plus 1. And what we're trying to figure out right now is under what circumstance would this be a perfect square? So I'm going to actually just kind of do a little chicken scratch here. I'm going to set this equal to something like m squared. This is where m is an integer. So we take an integer m, we're going to square it and basically set that equal to the average of our two numbers. Okay. Well, let's see. Anybody have any ideas what we can do with that? This is a little bit interesting.
Could we add or subtract a 1 on both sides so that the 2K plus 2 then becomes a prime?
I like that idea because, we know that prime factorizations have to be unique according to the fundamental theorem of arithmetic. And so if we have a single prime on one side, then we're going to have a single prime on the other side. Do you guys think it'll be a good idea so if we add 1 to both sides of this, we'll get P. If we subtract 1 from both sides of this, we'll get Q. Does anybody think there's a preference between adding 1 or subtracting 1 in this case?
I think I would choose -1 for this, for like how I would work it out.
So would I. I like that. And what's the reason? Like, why is it better to have a -1? Why do you prefer m squared minus 1 over m squared plus 1?
Because it's the difference of perfect squares or whatever it's called.
Exactly, Renee. We can factor a difference of squares. So that's going to just help us to it's going to be more transparent, easier to break it down. So let's do that. Let's subtract 1. I'm going to put this in a box, and I'm just going to subtract 1 on both sides. When I do that, I actually have Q on the left, and I have m squared minus 1 on the right, which is m minus 1 times m plus 1. Isn't that interesting? We actually have a prime, which is Q, but it's being represented as a product of 2 numbers now. What does that tell you, knowing the definition of a prime? What does that tell you over here about this factorization? Doesn't it basically mean if Q is a prime, you cannot factor it except trivially? So one of these 2 factors has to be 1. And it's going to be the smaller one. By the way, we may as well assume that m is positive to begin with. So we're not multiplying 2 negative numbers here. These are basically, m is definitely going to be a positive number. So the smaller of the 2 numbers is m minus 1, right? So since Q is prime, m minus 1 has to equal 1, and m plus 1 has to equal Q. That's the only way to do it. And so m is 2, that's easy. And so Q is 3. That's also pretty easy. And as soon as Q is equal to 3, then P is equal to 5. So actually, there is only one pair of twin primes. There's only one twin prime example where the average is a perfect square. There's no other way to do it. It's kind of interesting. And it's done by, it's a nice problem because we're using the definition of a prime to do it, which is something we rarely actually explicitly use. So often it's the properties of the primes that we're using, not so much more or less coming from this definition. So, any questions on this one? Okay. Does anybody have any other? We're right about just about 8 o'clock sharp here. Does anybody have any other questions for me? Just generally speaking, like I said, I have a lot of office hours still to go between now and Monday, so there'll be time to ask me sort of more personal questions in that context. But does anybody just have a sort of a broader question based on anything that you've seen tonight or anything like that? Everybody's all out of, well, you know, this has been very thorough. If you came both last night and tonight, you saw 4 hours of problems that covered just about everything. I won't say I did everything both nights. I did not do the fundamental theorem of arithmetic yesterday. I didn't do Wilson's theorem today, right? So there were a few topics that only made it into one of the reviews, but I think where you saw the most overlap, where the problems were meshing and kind of, you know, lots of examples were showing up with those ideas. That's the sweet spot of where, you know, you've got to be absolutely solid and you would be expecting similar types of questions on the test on Monday. I know some of this stuff like twin primes and, square free integers may seem a little random, like, oh gosh, how am I supposed to know what's going to get pulled out on the test, right? You have to trust me that I always try to be fair. Sometimes I get excited and I write a question and somehow I'm really into it, but then it just doesn't work. And that's more on me than it is on anything else. And I can always fix that later. But you have to trust me that I'm going to do everything I can to be fair, which means if I do want to bring something into a question that's kind of off the wall, I'm going to have to guide you. I'm going to have to give you a hint, or I'm going to have to put the appropriate background into the question so you know what the heck you're trying to do. But there won't be that much of, I haven't written the test yet, but I don't think I'm going to write a ton of questions like that where I'm bringing in something where I have to define a new idea or anything. That's not really, maybe one question I could do that, but that's not something I'm going to be doing a lot of. But certainly, yeah, during the test, if you have questions, just use the chat to talk to me. And if I can clarify anything, if there is something that does seem a little bit, off the wall from what we've talked about all semester, then maybe that would be something you want to just ask me real quickly. But otherwise, yeah, it's great to listen to me. I'm glad you're here and to learn as much as you can and see a lot of examples. At some point, I need to kind of be quiet and let you guys take your own limelight and see where you're at with the stuff. And hopefully you can grind through that sample midterm and just give yourself a little self-test here and see where you're at. Maybe sometime tomorrow you can take that test and then follow up with me if questions do come up, okay? So I'm gonna go ahead and kind of wrap things up. I will be posting this recording to an email. I'll send that out to you guys in a little while. And then I'll be going over to my Zoom office hours. So I hope you guys got something good out of this. I hope it was useful. And I look forward to helping you out more if you need it. And I wish you all the best with the rest of the weekend and getting the studying done. So that's it for now, guys. Thanks for coming. And we'll take a little break and we'll talk again soon. All right. Bye, everybody.
All right. Thank you so much.
You're welcome.